This is the solution video for question 20 from section B of the 4th sample test for CSAT. In this question, we're told we're given a language which has the following two rules. That B is a word, and if X is a word, then BBB, XXX is a word. And given this, we're asked to firstly give an expression for the number of B's in a valid word. So we can fairly easily see that any word we create in this way is just going to be a string of B's of a certain length. And once we've got to a string of B's of a certain length, we make the next longest word by substituting that string in as X. So we know, firstly, that if we've got a word with KB's in, then the next word create, we sub in that word XXX, so we get 3KB's and then the 3B's here. So we get a string of 3K plus 3B's in the next word. So algebraically we can, or in a sequence we can represent it as this. Li is equal to 3Li minus 1 plus 3, where Li is the number of B's in a word, and we'll make L0 B, because that's sort of the starting point, so it makes sense. But you could change that index. You could make L1B if you wanted, and it won't make any difference. But we're going to go for L0 is B. So how do we get anywhere from here? Well, we know that essentially this relationship's true for Li minus 1. So if we substitute that in, we have 3Li minus 1 plus 3 is equal to 3 times 3Li minus 2 plus 3 plus 3. So just substituting this into here, but for I minus 1. Which implies to this, 3 squared Li minus 2 plus 3 squared. And you can probably see where this is going, because if we did this again, we'd do a similar thing, and if we did it I times to get to L0, because we know what L0 is, we get 3 to the I, L0, plus the sum from k equals 1, so 3 to I, because we're at 3 squared when we're looking at Li minus 2, so at 0, which is Li minus I, so to speak, go up to I, sum of 3 to the k. So this is technically an answer, this is a valid expression, but it's not the nicest looking thing. But the thing to notice is that this is geometric progression, and we know that for a geometric progression, if we sum up to n terms, it's a over r, a times r to the n minus 1 over r minus 1. And we can do that here. So we know this is 3 to the I, we know L0 is 1 because it's just b, so we'll just put that in, plus 3 times 3 to the I, because common ratio 3, minus 1 over r minus 1, which is 3 minus 1. And then we get, if we put this over 2, gather up the 3 to the i's, we've got 2 3 to the I over 2 here, 3 3 to the I, so 5 times 3 to the I minus 3 all over 2, and we have our result. We've got a general expression for the number of B's in a valid word, and it's this, as I varies between the positive integers and 0. The next part of the question, B, says to suggest a third rule such that all multiple of 3 B's and B itself are valid words, and they are the only valid words. So the key to this is recognising what Li is, and the question we want to ask is, does our current rule 2 only give things that are multiples of 3 as words? Because that makes constructing rule 3 a lot easier. And it does, because we can rearrange, we can take a factor of 3 out. So 5 to the 3i minus 1 over 2 times 3. So if this thing's an integer, we know all the words we currently build with 1 and 2 are multiples of 3 in length. And indeed it is, because we know 5 times 3, we know 3 to the I minus 1 is odd, 5 is odd, so this is odd. This minus 1 is even, so we're doing even divided by 2, so we're going to have an integer here. So we know that following rules 1 and 2, we only generate multiples of 3, but we won't get them all. But we can certainly make arbitrary big multiples of 3, just by doing it again and again and again. So the things you're allowed to do with this third rule aren't particularly clear, but probably the one most in keeping with the style of the question is this, that if BBBX is a word, then X is a word. So how does this work? Well, certainly if 1 and 2 only generate multiples of 3 length words, then this is just going to give more multiple of 3 length words, because if we have a word here and we take 3 off it to get the new word, and it'll also get to every multiple of 3, because pick any multiple of 3 you're scared you're not going to get to, we know we can construct a word with 1 and 2 that's bigger than that, and if we just use 3 enough times, we'll get down to it. So this is probably the most apt rule in keeping with the style in 1 and 2, but it's quite a few things you could have put here to satisfy this criterion. The final part of this question, C, asks us to replace the rule 3 we just came up with by the rule BBBBX is a word implies X is a word. And given this, we're asked to find all pairs P and Q such that for all integers n, Pm plus Q gives the length of all valid words. So the first thing to look at is we want to apply 2 and 3, but preferably mixing up rule 2 and 3, saying applying rule 2 and rule 3 twice and rule 2 is messy. It'd be useful if we could group them together. So we apply rule 2 I times and then rule 3 K times say and look at the results from that. That's easier to look at. So first thing to know is if we do rule 3 then rule 2 and we have a word with KBs where K must be bigger than or equal to 5 for it to make sense. If we do 3 then 2, we go to K minus 4Bs as our word, then we apply 2 and we get 3 plus 3K minus 12Bs, which is 3K minus 9. So that's what happens when we do apply rule 3 then rule 2. But then if we do rule 2 then 4 lots of rule 3, we go from KBs to 3K plus 3Bs to 3K minus 9Bs. So what we've shown is that if we do rule 3 then rule 2, we can just replace that in our procedure of building our word by doing rule 2 and then rule 3 4 times. So how is this helpful? Well, it means that when we construct any given word with our rules, we can assume that we just do rule 2 first, however many times, and then rule 3 however many times. And we know that gets to all the possible words we could construct. And that means it's a lot easier to keep tabs on the length of the word. So bearing what we just did in mind, what we can say is that we can build exactly the words of this length for I and n integers. Why is that? Well, we know from our rule 1 and rule 2 we can build anything with this length and exactly this length. This is what we did in A for a given I. But remember, by what we just said with showing that 3 then 2 is replaceable by 2 then 4 lots of 3, we can assume that we do 1 and 2 first lots of times and build a word and then just apply 3 so many times to get to our aim. So we know this, and then we take away 4n for n applications of rule 3. And so we know any word must be of exactly this form, of this length. So now we've got this, what do we need to look at? Well, we need to see, can we make P and Q so as we vary M, we can write this. So let's look at general lengths of words we can make. Maybe we can make some deductions on what P and Q might be. So we know we've got a word of length 1. And if we apply rule 2, we get a word of length 6. And then let's try and decrease it. So if we apply rule 3, we get a word of length 2. So this tells us a lot about P and Q actually, because it tells us that if we've got a word of length 1 and a word of length 2, if the difference between two valid words is 1, P has to be 1 for this to work. And similarly, if M is 0, and we know we've got a word of length 1, Q has to be equal to 1. So our only possibility is P is 1, Q is 1, and we have to check if this works. But what this basically means is that if P is 1 and Q is 1, it's essentially saying that all the valid words are, we can make a word of any given length for a positive integer. So that's what we need to look at. Is it true that we can make any word length for any positive integer? So there's a couple of candidates that it doesn't seem obvious to make. It doesn't seem obvious how to make a word of length 3, and it doesn't seem obvious how to make a word of length 4. The one we're going to go for is 4, because we can change our question to this. So the question we can ask is, can this 5 times 3 to the I minus 1 over 2 times 3 be a multiple of 4? Because if this isn't true, that we can't make this a multiple of 4, we're certainly not going to be able to make a word of length 4 by taking away lots of 4. So if the answer to this question is no, we know this P and Q do not work. So now we have this question to answer. We can change it up a little bit, because this is the same as this. Because this being a multiple of 4, it doesn't matter if we times it by 3 or not, because 3 and 4 are something called co-prime. So that means 3 doesn't go into 4 and 4 doesn't go into 3. And they don't share any common factors. So we can just look at this top bit, this bit here, and ignore the 3. And we'll see 5 to the 3 to the I minus 1 minus 1 over 2 is a multiple of 4, if and only if when we times it by 2, it's a multiple of 8. So we need to ask this question, can this be a multiple of 8? Now, the answer's going to be no, but why? Well, what we essentially need is this. So if you see modular arithmetic, it's by adding 1 to both sides with the mod 8 equation. If not, what this means is this is a multiple of 8 if and only if when we divide this thing by 8, we get remainder 1. So read this as saying this is the remainder when we divide by 8. So if we divide this by 8, get remainder 1, then this is a multiple of 8. So we need to check, can this be true for some I? So let's try some i's. So if I is 1, 5 times 3 to the 0, so 5. 5 divided by 8's remainder is 5, so we get 5 mod 8 is 5. What about I equals 2? Well, we can do it a couple of ways, but 5 times 3 is 15. 15 divided by 8 gets remainder 7. So 15 mod 8 is 7. And I equals 3, so 5 times 3 to the 2, so 5 times 9 is 45. We know 8 times 5 is 40, so we know the remainder if we divide 45 by 8 is 5. So now we see 5, 7, 5. And if we carried on doing this, essentially we get 7, 5, 7, 5. The cycle would continue if we made I bigger and bigger, which sort of makes sense because divisibility only really matters in the remainder. It doesn't matter if we add lots of 8, etc. But in any case, we know we're never going to get a 1 here. So from this, what we know is that no such I exists to make this true. And that means that this thing is never a multiple of 8. So this thing's never a multiple of 4. So what we've shown is that with our rules, we can never make a word of length 4. So P equals 1 and Q equals 1 can't work. But P equals 1 and Q equals 1 were the only options we really had left to try. That's what P and Q must be. So what we must conclude is no P and Q exist, and we're done.